So let's think now about how to model the technological constraints of the firm. And the idea of the basic model is very simple. Think of the firm as a black box that has a production technology. And what the production technology does is it takes inputs of production, let's denote them by the first input to the last input. This is the level of each input. It passes them through the production technology and it produces output that we're going to denote by Q. That's the general representation of a production technology. Now, in general models, in economics, there are many different types of inputs, capital of different types, machines of different types, labor of different types, land, etc. For the purposes of this course, we're going to think of there being, it's a simplification, only two types of inputs, K and L. K denotes capital, and L denotes labor. And you should think about the labor as just basically the amount of workers, and capital, some sort of the amount of machines measured in some machine unit. So what we're going to have is a production technology that takes a certain amount of capital, a certain amount of labor, and kicks out an output. And we're going to denote the general production technology by a function f k of L that tells you for any amount of k and any amount of L, what's the amount of Q that gets produced. It's a two-dimensional function. Now, graphically, we can represent the function in, this is the domain of the function of K and L. The amount of capital is coming out of the screen. And we can represent the function by its level sets. It's actually something very useful to do, as you will see in this unit. Think of the, for example, level sets of the function like this. These are each level set is the set of combinations of capital and labor that produces the same amount. So all of this, for example, is the amount of combination of capital and labor, let's say, that produce an amount Q1, all of the ones that produce an amount Q2, all of the ones that produce an amount Q3, and typically it will increase the more capital and labor you have. By the way, each one of these lines with equal production is called an isoquant. An isoquant. Let me introduce you to two basic concepts that are very useful in thinking about production technologies and describing them, and that will play a role in solving the problem of the firm later on. One is called the marginal product of capital, which we're going to denote by MPK, and is defined as the partial derivative of the production technology with respect to capital. And if you think about what that means, it's just the marginal change in output, the F, induced by a marginal change in capital, the K. So think about it intuitively is what happens to output when we increase capital by a tiny bit while holding labor constant. What is the change in the F? Intuitively is a measure of the productivity of capital locally at the margin. A similar concept is the marginal product of labor equals to MPL, and is just analogously to the partial derivative of the production technology, or the production function with respect to labor, and is analogously just the marginal change in output, the F, induced by a marginal change, the L, in the amount of labor used. And for the same reasons, you can think about it as a local measure of the productivity of increasing labor. Now please notice that the marginal product of capital and the marginal product of labor are always evaluated at a particular point in the production space. So for example, you may evaluate it at this combination of capital of labor, or you may evaluate it there. And the value of the marginal product of capital and the marginal product of labor may be different at these 2 points. And in particular, notice that the marginal product of capital may be affected by the amount of labor that you are consuming, that you're using, and vice versa. So for example, it may be that the marginal productivity of hiring an extra worker depends on how many machines you have. It may be that the marginal productivity of hiring an extra worker when the level of machines is low, let's say there, K low, the marginal productivity of hiring an extra worker is low, but when you have a lot of machines, when K is high, the marginal productivity of hiring an extra worker gets larger. That interrelationship between capital and labor in their marginal productivity is something very common and something that will be interesting and we will look more at later on. Now let's talk about some basic properties of the production technology. One property that we're going to call productive inputs, the assumption or the property of productive inputs, basically says that the marginal product of capital and the marginal product of labor are greater than zero. The intuition of this assumption is trivial. It just basically says that adding more capital or more labor, adding any input of production, always generates more output. Very natural one. The one that is more interesting is one that we're going to call decreasing returns to scale. And important, not always, just eventually. And let me be precise. They are eventually decreasing returns to scale. Let me be precise about what this means. It says that if you look at the impact or the marginal impact on the marginal product of capital of increasing K, in other words, how is this marginal product of capital changing with K, is less than zero for sufficiently large K. So it doesn't have to be everywhere that this property is true. It's only when K is already large enough. And the same thing for labor. The marginal derivative with respect to labor of the marginal product of labor is negative for sufficiently large L. Let's look at some examples to really get an insight into what the assumptions mean, especially this second assumption. So I'm going to draw for you over here 4 different production technologies, and to be able to draw this easily, I'm going to assume that labor is fixed at L bar. So I'm basically only going to plot how the function is changing with K. The first one looks like this. So as a function of K, this is to remember the level of output, it's just a linear function like this. The second one is going to look like this. It's a function, okay, it's concave, it goes down like this, it bends back. The third one is a function that looks like this. It explodes up. And the fourth one I'm going to draw here is the more important or more interesting one in some sense, is one that first increases and then it bends down. Okay? So let's think about whether these functions satisfy these properties. First look at productive input. In every case, as you increase K, the amount of output produced goes up. So all of them satisfy the assumption of productive inputs. Now let's check whether they satisfy the assumption of eventual decrease in returns to scale. Let me start with this one because it's easy to see. Here, the marginal product of capital, which is just going to be the slope of this curve of the production function, is clearly going down. It's becoming flatter and flatter. So this one satisfies it. This one actively violated, since as capital increases, any additional marginal increase in K increases output by more and more. In other words, the slope of the production function with respect to K, which is the marginal product of capital, is getting larger and larger. So this actively does not satisfy it. What about this one? The slope of the production function with respect to K, which again is the marginal product of capital, is constant, so it never goes down with K. This derivative never becomes negative, so it doesn't satisfy it. What about this one? So if you think about it, the marginal product of capital, which again is the slope here, is increasing for a while, keeps getting larger, but eventually when you reach a certain threshold, it starts going down and it always keeps going down. So it doesn't satisfy that this derivative is less than zero for the entire range of capital, but eventually it does. So this one satisfies it too. Now, what is the assumption? What is the economic intuition that justifies this assumption? What is the key idea behind the assumption? The key idea is that somehow there is some optimal scale of production. There's an idea behind it is that all technologies have an optimal scale of production. That in this case, it may take a while to reach, but eventually you reach an optimal combination of K and L, and adding more of the factor just is not as productive because it is kind of an optimal recipe, an optimal combination of putting together the inputs for being maximally productive, and beyond that, things are not just as productive. That is the key idea here.
Let me introduce you to a taxonomy of production functions that is very common in the literature and very useful. We're going to consider three classes of production functions. The first one are called constant returns to scale. Constant returns to scale. Production functions of this type satisfy the following property. For all pairs of inputs K and L, and for all lambda, which is some number greater than 0, we have that if I take the original level of production at f of KL and I compare it with what gets produced at the level of inputs lambda K and lambda L, I get exactly lambda times the output. In other words, if I double the inputs, I double the level of production. And that happens for any change in the scale that I may consider. The second case is called decreasing returns to scale. Decreasing returns to scale. And that says that for all K and L, and importantly, for all lambda greater than 1, not greater than 0, greater than 1, if I compare the initial level of production and I ask what happens when I amplify the level of inputs of production by a factor lambda, let's say I double them, I get less than lambda times the level of output. In other words, intuitively, the outputs scale less than linearly with the inputs of production. And the final type, and you will see immediately the analogy, are increasing returns to scale. That says that for all K and L, and again for all lambda greater than 1, if I compare what happens at the initial level of output when I scale the inputs, again, say by a factor alpha, now I get more than linear scaling. So for example, if I double all of the inputs of production, I more than double the output of the production function. Let me give you some examples to nail down the concept. So let's consider some simple production functions that only depend on labor. And I'm going to draw for you one that satisfies constant returns to scale, one that satisfies decreasing returns to scale, and one that satisfies increasing returns to scale. And again, in every case, the only input of production is labor. So one that satisfies constant returns to scale is going to be basically some sort of line through the origin. One that satisfies decreasing returns to scale is going to be a function like this, let's say square root of L, for example. And one that satisfies increasing returns to scale, it may be something like this, let's say L squared. And let's see why they satisfy the properties. So for example, let's look at the first one. Let's say that we start at this level of labor and we double the amount of labor to 2L bar. What happens? If the initial level of output was here, now we have double the amount of output. And it is easy to see that because the production function is a line through the origin, that will happen regardless what factor lambda we use, 2 or anything else. Now, ask yourself what happens in this particular case. So let's say we are at L bar, and this is the level of output f of L bar. And now we double as before L bar. Now, if things scale linearly, we should have been at this point. But instead, we end up being at this point. This is f of 2L bar, which is less than what we have gotten here, which is 2 of f of L bar. They are decreasing returns to scale. Increasingly amplifying the level of inputs amplifies the level of output by a factor smaller than that. And immediately, I'm going to belabor less on this case. You see that the opposite is in this particular case. If you double the level of inputs, the level of output that you get is more than twice the level of output.
I want to emphasize that there are production functions that do not satisfy any of those three properties, CRS, DRS, or IRS. A production function can be neither of them. And let me give you an example. Again, let's stick with the case in which there is only one input labor, and suppose that you have a production function that looks like this. It initially increases quickly, and then it bends down. Okay? So we saw that example before. Notice that this function does not satisfy CRS, IRS, or DRS, because those are global properties. They have to hold at every point. And intuitively, this function satisfies increasing returns to scale here locally. So locally, if you scale production up, it increases faster than the scaling of the inputs, but then it switches to decreasing returns to scale. So locally too. So they don't satisfy IRS or DRS. By the way, I should put this in quotation marks because those are global properties that this function fails, even though locally, kind of intuitively, they satisfy that property. Let me give you an example of a specific production function that is used a lot in applied economics and in empirical work in trying to kind of estimate what the production function of countries, companies, regions looks like. It's called the Cobb-Douglas production function, and it's a function that looks like this. F of K and L is equal to A times K to the alpha, L to the beta, where alpha and beta are greater than 0. Now A, which is, if you can think about it, is a constant also greater than 0 that scales production up and down, is called total factor productivity, and it's called that because as you increase A, holding everything else constant, it scales up the productivity of the technology. Now, this production function is very widely used because when one looks empirically at the productivity of firms with a sufficiently aggregated notion of inputs, of aggregate levels of capital and labor, it fits the data reasonably well. So it has empirical validity. Now, I claim that if you draw a line with, and you look at what is the value of alpha and beta, and you put 1 here, at 1, when alpha plus beta is exactly 1, this Cobb-Douglas function satisfies constant returns to scale. That below it, it satisfies, and by the way, above 0, of course, because of this constraint, satisfies decreasing returns to scale, and that above it makes the function satisfy increasing returns to scale. I'm going to prove this to you for the case of constant returns to scale. You should, as a good exercise for you, do it more generally. So why does it satisfy constant returns to scale if alpha and beta are equal to 1? So suppose alpha plus beta are equal to 1. Now let's ask, what is the effect of multiplying by lambda the inputs? Substituting into the formula, we get that this is just A lambda K, because you have scale by lambda capital to the alpha, lambda L to the beta, but this is just equal to A of lambda to the alpha plus beta, K to alpha, L to beta, alpha plus beta and 1, so this is just equal to lambda A K of alpha L beta, but this is just equal to lambda F of KL. Okay? Now, if you want a graphical intuition for why when alpha plus beta are equal to 1, the production function satisfies constant returns to scale, and kind of what does that look like? Let me draw a figure for you. So I'm going to draw this in 3 dimensions, see if I can pull it off. Suppose that this is capital, that this is labor. Suppose that you're initially at a point like this, KL. It's going to be a ray that goes from the origin through the point that we were looking at. Let's say this K bar, L bar. Okay. Now, the idea is that we can then look at the plane that is above that ray, let's see, a plane that looks like this, we can ask, what does the function look like on that plane? Okay, we can plot the function on that plane, and then we can ask what happens as we multiply production, as we scale up production, let's say from this initial point by multiplying by lambda to this initial point, which is going to be lambda k bar L bar. We're just scaling up and down. Well, when alpha plus beta is equal to 1, the function is linear along those rays. Now what is beautiful is that, for example, when k is equal to 0, the function is here. When it's equal to L, is in that axis. So it kind of looks like a conical section that is flipping there. But along any ray, it looks like a straight line. And that's why it satisfies constant returns to scale when alpha plus beta is equal to 1. Now, many functions satisfy what is called a minimal production scale, which is an important and intuitive concept. To make it concrete, consider a function, a production function, again, that only depends on labor. Ignore capital for a second. And the idea is that there are production functions that have this qualitative feature. So if I put here L, the idea is that there is a minimum amount of labor, a threshold amount of labor, let me call it L bar, below which the output is 0. The production, you cannot produce anything. And then above that, maybe, for example, it goes linear, or it may bend down. But only above that is hiring extra labor productive. Okay? Now, the equation for this production function would be f of L is equal to 0 if L is less than L bar, and then let's say beta L minus L bar if L is greater or equal than L bar. So you can think of beta as the slope of that line. Now, what is the intuition behind this type of production function? The basic intuition is that it takes L bar units to basically set up the basic infrastructure of the company, to really put the buildings, plug the machines. Even before you start production, you need to spend this much inputs, this much labor inputs to really get something from which you can start producing. You wish getting the building, the factory ready. And it's only these extra workers on top of that that can become productive. Now, one interesting property of the presence of these minimal production scales is that it leads to production technologies that exhibit something that qualitatively looks like increasing returns. And the best way to explain it is with a concrete example. So suppose, let's say that you are at a firm and you have hired this level of workers. Let's call it L hat. How much are you producing? You're producing this much. Why? Because of all of these workers, only this many are engaged in productive activity. Now suppose that you double the amount of workers that you have. So you go from L hat, let's say, to L hat. Now how much do you produce? Now you produce this much. It's clearly that is more than double. And that is why it looks like increasing returns like behavior of the production scale. What is the intuition for why the minimal production scale generates that? Well, is that the first L bar workers, once you have paid the cost of hiring them to plug the machines, they don't need to be hired again. And therefore, every additional worker that gets hired after that can take full advantage of that. So if you wish, that spreads out the cost of these workers among more productive workers, which increase the productivity.